Hi, this is Aaron Jerome from Jerome Electronics, a YouTube channel. You're listening to a song sung by Don Walzer. He was probably the world's best yodeler. This is a song that was included with the movie Second-Hand Lions. I wish I could play you him yodeling, but that's a little further into the song, and we need to actually get on to what we're talking about. We're going to be talking about combinational logic practice. So, combinational logic practice, this presentation is a review of how to capture your own ideas and turn them into real marketable products. Much like what we did last time, we have 3 worksheets that students will use as they follow along in this presentation. This is one of them. This is another one of them. We're just practicing our ideas here. And then there's an assignment that I actually have them design, build, simulate, turn in, all that. And we'll be getting to that as well. So, students, remember, you are the one that decides what you want the output of the truth table to do. This means you can use truth tables to capture your ideas and develop your own circuits. So, procedural review. You're going to think of a great idea. You're going to write the idea down. You're going to define the inputs and the outputs. You're going to state the true or false question that's answered by each input. You're going to create a truth table from the information that you've developed so far. You're going to extract the Boolean expression. Actually, you're going to extract the terms, combine them to make a Boolean expression, and then combine them into an equation from the truth table. From there, we'll talk a little bit more about simplifying the expression. Later on, we'll use K-maps, or algebraic simplification, but we won't be getting into that quite yet. We're going to do the rest around it, and I will provide the simulation or the simplifications. Next, we're going to draw the schematic. We will not do that in this presentation, but we will eventually build the circuit, the prototype, and sell the idea for big bucks. So you don't need to write these down because this is just a review of what you've written down previously. So we're going to move on. I'm sure that if you all had the right resources, you'd probably be working on your DeLorean levitating time machine in your spare time. One day when you are flying around in your DeLorean levitating time machine, the door came open and you almost fell out because you forgot to put on your seatbelt. In your mind, you began to develop a solution to this problem. You wanted to design an alarm system that works only when the machine is running, and that means the key is in the ignition. And we can represent that if we use a sensor to tell whether or not the key's in the ignition. And when the door is ajar, of course, that means that the door is slightly open. And of course, because either condition is dangerous, when the seat belt has not been fastened. How many sensors are we going to need? We're going to need 3. We're going to need a key sensor, a door sensor, and a seatbelt sensor. And remember, sensors are really, in this case, sensors are really just switches. For example, we might use a key sensor like this, so the key actually presses the wires together, allowing the voltage to flow through, and that's interpreted as a 1. Or we might use this sensor that is always a 1 unless the door is, well, it's always a 1 when the door is closed here. And if the door is open, it's always a 0 when the door is closed. And when you open the door, it connects the circuit and sends a 1. You don't have to use this kind of a switch, but you do need to make sure that you know what kind of switches you use. This is an always on unless the seatbelt is fastened, and then it shuts off. Remember, each of these switches can determine whether or not what kind of a question that we use. So input sensors answer true and false questions. For example, a question we might ask is the key in or is the key out? Is the door ajar? Is it open? Is it shut? Is the seatbelt fastened? Is it on or is it off? And should the alarm sound? We have to decide when the alarm will sound. We're going to be using combinational logic. also known as AOI logic, because A stands for AND gates, O stands for OR gates, and I stands for inverter gates. So if we use an AND gate, that's an 08. If we use an OR gate, that's a 32. And if we use an inverter or a NOT gate, that is an 04. Okay, and you have a copy of this worksheet, and what we're going to try to do is decide when the alarm should sound. When would an alarm warning be helpful? So we kind of have to decide what each switch response means. So in this case, we're going to decide that a 1 means the key is in the ignition, a 1 means the door is ajar, and a 1 means the seatbelt is fastened. And we have done something similar to this before, I believe, and but this is going to be a different result because we're changing the questions. We need to decide, when will the warning alarm go off? Okay, I'm entering the index row here off to the side and also saying, okay, a 0, what does a 0 mean? 0 means the key is out. Key is out is a 0. Key is 1 is an in. The ignition key is out. It's a 0. The door. What does a 0 mean for the door? That means the door is ajar or slightly open. So that could be dangerous, but not dangerous if the key's not in because we're not moving. So the door is closed because a 1 means the door is open. And the belt is off. Belt is a 0, and 0 means the belt is not on. And the car is empty. Key is out, the door is closed, the belt is off, the car is empty. What should our response be? Do we need an alarm if the door's closed, the seatbelt? No, the door is just sitting there. The car is probably just locked. So we don't need an alarm for that. What about the next row? Now this is where you want to pause the video and see if you can fill out the outputs of this truth table as well as the index column and see if you can get the same result that I did. So hit the pause key, see what you can do. Now I'm not going to hit the pause key, so I'm back online, and so we're going on row 1, according to the index. The key is still not in. The door is still closed, and the seat belt is on. And do we need an alarm for just getting in? When you open your car door and the door's closed and the belt's on, do you need an alarm to get in? Probably not. Key is out, door's open, belt is off. Do we need an alarm for this? Probably not. You're just getting in. In fact, every time that the key is not in, there's no danger. So basically the key's out, the door's open, the belt is on, you're getting in still. Next one, the key is in, which means that there's the potential that we're flying around in this hover car. It says the door is, the key is in. The door is a 0. That means the door is closed. The seatbelt is a 0, which means the seatbelt is off, not fastened. So we're flying around, the door's closed, but the seatbelt's not off. We generally already have an alarm like this in our car. So yeah, it's probably a good idea to have the seatbelt warning warn us to turn to put our seatbelt on. Okay, next situation, next combination. The key is in the ignition, meaning that we could be flying around. The door is closed because 0 means the door is closed, and the seatbelt is on. No, just driving around. It's safe. Don't need a warning for this one. The next one, 6, the key is in the ignition, the door is open, and the belt is off. Do we need a warning for this? Well, yeah, the door is open. We're flying around, seatbelt's off, the door is open. Yeah, it's probably a good idea to get a warning for this one. Last combination. The key is in the ignition, which means we could be flying around. The door is 1, the door is open. That's dangerous. The seatbelt is on though. But still, it's probably a good idea to say, hey, the door is slightly open. We probably ought to make sure that it is closed before we continue. And so we're going to set an alarm for that. These are different terms that we're pulling from this truth table. Same kind of an alarm as we've done before, but different terms. Now, we are going to try to put the Boolean equation for this, and then I will provide the simplified equation. This is a good time to pause the video and see if you can pull each term out of the rows that end with a 1, combine them with OR gates, and make them equal to something, make the equation, the unsimplified one. Okay, so we're pulling terms out of these 3 rows. The quick way is to just put the KDB there, K for key, D for door, B for belt, and then look back through the inputs. Wherever there's a 0 on the inputs, you put a line above the variable for that. So there's K not B not D. Next we'll have K, D, not B. And finally, nothing is knotted on this last row. So we're building the equation now, KDB, 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 and putting the knots above them again. We're making it equal, and we are combining the terms with OR gates, or we're adding them together. Now, just so you know, we haven't actually learned how to do this, but the simplification for this is KD, X equals KD, plus K not B. Okay, so I'm going to go through this again, and I'm actually going to show you a circuit here and show you why X comes on when you build this equation just as it is shown. So we're asking, why does this light come on with this configuration, this simulation, but with this configuration of gates? We're going to step through each one of the row combinations to see why the light comes on when it does. Now, don't be confused by the red line after the NOT gate, because we're not putting any pressure in, we're not putting any volts in. The NOT gate inverts that to pressures coming out. Okay, so just be aware that's what that means. Now with row 0, this is the standard for that. This is what the results are. K is a 0, so K, if it were pressurized, this gate would flip up here and the pressure would flow through. But it's not pressurized. All gates are off, meaning that this is a 0 or a not K, and this is a not D or a 0. 0 times 0 is 0. And down here, K is also a 0, and it's being multiplied by B, which is a 1. 0 times 1, the result of that is a 0. So 0 plus 0 is 0, and that's our result. The light is off, just as it is shown in the truth table. Now, switching to the next row, what we have done is we have switched B to a 1. What does that do? Well, that actually pressurizes before the NOT gate and drains after the NOT gate. Not much of a change. Nothing else has changed, so that light still is off. Let's go to the next row. We've turned B off. When we turn B off, and we've turned D on, so what's happening? Well, when we turn B off, B as in boy, that depressurizes the line before the NOT gate, which pressurizes the line after the NOT gate. The D is on, which means the D line is pressurized, and that is all. And so what we've got is on the top AND gate, 0 times 1 is a 0. On the bottom AND gate, 0 times 1 is a 0. And so zeros flow through to the OR gate, and 0 plus 0 is still 0, which is demonstrating that the light is not coming on. Let's go to the next row. Here we're going to turn on both B and D, but I'm doing one at a time for illustration purposes. B is on, which means the line, the wire before the NOT gate is pressurized. We also call that a conductor or a net. That means that after the NOT gate, the line is depressurized. Now we're going to turn the D line on. That pressurizes D. They're both on, and still nothing gets through the AND gates because we've got 0 times 1 for the top AND gate. That results as a 0. And 0 times 0 for the bottom. That results as a 0. So 0 plus 0 is still 0, and the output X is not on. But as you can see on the truth table, that output X is about to come on with combination row 4. Switching to row 4, we're actually depressurizing now the B line, which means after the NOT gate, the line is pressurized. Also, we're depressurizing the D line, D as in dog, and then we're pressurizing the K line. Now that K line splits and goes in 2 directions. The upper stream does nothing because that is a 1 times a 0, but the lower stream happens to be a 1 times 1, and 1 times 1 is 1, which pressurizes the line going into the OR gate. Even though the line at the top of the OR gate is a 0, 0 plus 1 is 1, and that results in a 1 that lights up the light. Going to the next row. In this next row, we are actually turning B on and leaving K on. What does that do? Let me show you slower. B on pressurizes before the NOT gate and depressurizes after the NOT gate, meaning that, let's go back to it, on the AND gates, those are all 1 times 0, that's 0, 2 zeros going into the OR gate, 0 plus 0 is 0, and that's why the light does not come on. Going to the next one. In this one, I've turned off the B line, which depressurizes before the NOT gate, but pressurizes after the NOT gate. And for that reason, since K is still on, we've got a 1 times 1 in the lower AND gate. That results in a 1, and 1 plus 0 actually is a 1, and that activates the LED. Last row. We're turning all 3 of them on. In this case, we have K that's on. And, it's the second to the last row. So on the second to the last row, we turned D on and left B off. What that did, let's go back and do it again. No, go in the wrong direction. What that did was it pressurized the line, allowing 1 times 1 through the top AND gate, which results as a 1. There's still a 1 coming from the lower AND gate, and going through the OR gate, 1 plus 1, true plus true, is true, and so that's why that LED is coming on there. Last combination, all 3 on. That means we're depressurizing before the NOT gate. Now we're pressurizing before the NOT gate and depressurizing after, but the light doesn't go off because of that, because the top AND gate hasn't really changed. Both of the inputs to that AND gate are pressurized or 1s, which means a 1 flows through, and 1 plus 0 is still a 1, and so that light is still on. Hopefully that helps you understand why all of these rows are actually functioning correctly as we set up the circuits. Turning everything off. If we turn everything off again, that pretty much drains everything, and there we are in the state that we were in just before we started. Now, hopefully that's helped you to understand that, but let's actually go through an example again that's different than any of the examples that we've talked about before. With this example, we've already, you have to realize that if the door is open, anytime the door is open, we want that buzzer to sound. Why? I don't know. Just a variety, I guess. So anytime the door is open, the buzzer will sound, or if the key is in the ignition and the seatbelt is not buckled. Okay? Just a different set of combinations, different set of expectations. We've also defined the seatbelt. 0 is not buckled, 1 is buckled. The key, 0 is not in the ignition, 1 is in the ignition. The door door is closed for a 0, and door is open for a 1, and the buzzer means off if it's a 0 and 1 if it's on. We're going to set up the index rows now just to make sure that we're all clear on which row we're talking about. Row 0, we're going to say the buzzer's off. Why? Well, the door is not open is the most obvious reason. The door's not open. This door is 0, door is closed. Anytime the door is closed, no buzzer. Okay, next one. Now, this is a good time to pause the video, see if you can predict these using your worksheet before I actually show you the answers. Pause the video here, get back to it in a minute. Okay, what did we decide? Well, we decided that this is a 1. Why? Well, because the door is open, and anytime the door is open, it's a 1. Now, the buzzer would have gone off also in row 0 if the key was in the ignition, which it is not, and the seat belt was not buckled. Well, in this case, the seat belt was not buckled in row 0. But it has to be both the seat belt's not buckled and the key is in the ignition. Okay, so let's go to row 2. In this case, the seat belt is a 0. That means the seat belt's not buckled. That seems kind of dangerous. The key is in the ignition. That seems kind of dangerous because the key's in the ignition, the seat belt's not buckled, but the door is open. No, the door is closed. It's door, not open. Door is closed. Okay, so is this a situation? Door's closed. Well, so if the door's closed, we wouldn't exactly turn it on, but the key's in the well, let's see. I'm sorry, I'm looking at it the wrong way. The door is actually closed, and the key is in ignition. Key is in the ignition. The seatbelt is not buckled. That is when we would normally turn on the alarm. Door is closed. What would we do? Well, we're going to sound the alarm here because even though the first condition was not met, the second condition was. What about row 3? Seatbelt, same as before, only this time the door is open. Even more dangerous of a situation, so we're going to sound the alarm. All right, in this case, the seatbelt is buckled. Key is not in the ignition. That's kind of safe. And the door 0 is closed. This is a safe situation. Next one, 5. The seatbelt is buckled. The key is 0. It's out of the ignition. Seatbelt's buckled, key is out of the ignition, and the door is a 1. Door is open. That's a dangerous situation. Okay, because we said anytime the door is open, the buzzer should come on. Next, the seatbelt is buckled, the key is in the ignition, and the door is closed. That's a safe situation. Last situation, the seatbelt is buckled. The key is in the ignition. So far, no problem there. The door is open. And anytime the door is open, that's an unsafe situation. So notice we've got 5 terms that we're going to pull out of this. Depending on how you define what the switches mean and the definition, how you define the problem, you could get kind of the same scenario, but different equation. Let's pull the equation out of this now. Or do we even need to? Maybe I won't pull the equation out of this. Well, I'll just talk about it. We would actually pull the equation SKD 5 times. We add all of those together, make them equal to B, and that would give us the unsimplified equation. So, incidentally, just so you know, when we simplify this, the result would be D plus not SK. So it is highly simplifiable. It's down to D plus not SK. But instead of continuing with that, what I want is to continue with this. What I need for you to do is, in your car, you want the alarm to sound. This is the worksheet that you'll be handing in, okay? So I need you to do this on your own. I will, of course, go through it in class. But you want the alarm to sound if the key is in the ignition and the seatbelt is on. Or if the key is in the ignition and the door is not closed. So there's two conditions here and two conditions here. Definitions: if the key is in, that's a 1. If the seatbelt's on, that's a 1. If the door's closed, that's a 1. Complete the truth table. Next thing you're going to do is pull the unsimplified equation and list it below. I have already given you the simplified equation, that is B equals not dk plus k equals not s. But you're going to take that unsimplified equation and you're going to list it right here in this space. Then you're going to go to the simulator. You're going to use the computer simulator like Multisim. You're going to pull up the bus template that you've already created earlier. And you're going to place the output probe, AU, next to the input probes here. And this is for the unsimplified result. Over here, you're going to put another probe in a completely different circuit where you're going to wire up the simplified version. And see if you can do that without my help. Okay. So there's your assignment. Work on it. You're going to also, below the unsimplified, you're going to simulate the simplified solution, which is this one that I've already given you. Make sure all the output and input and output probes are aligned horizontally. That's what this means, because this represents the truth table. These are the inputs and these are the outputs. Okay. Make sure you use elegance in your design. We've explained that earlier. Make sure you're not making a tangle of spaghetti. And then you need to verify that the simulation outputs match the truth table outputs for each row. Zeros and ones must all match what the truth table predicts on your simulation. Verify that the equations are equivalent in value. That means that A unsimplified and A simplified should always light up at the same time. And they should only light up when the truth table outputs say they should. Now, once you're done, you're going to ask your instructor to check your work, and then you're going to print your simulation on a single page. You know how to do that. Attach the printout behind this sheet and turn them both in for points. So anyway, that's what I want you to work on. That's your assignment. And that's all I've got to say for now. Aaron Jerome, Jerome Electronics YouTube channel. Talk to you later.